Here we go. There you go. So this is what we're going to have a look at now. So just like the first lesson, this is not so big of a topic, this one. Equilibrium of coplanar forces. You got the title?
Yes.
Yep? Okay. Come on. There we go. Now, have a look at this picture. Although it doesn't look like it, this is a special type of problem in physics. And the reason I'm saying it's special, even though it doesn't look special, is because there are three forces acting on the system. So do you see there are three forces? The first force is the weight. The second one is the reaction from the wall. And then the third one here is the reaction from the ground. So there are three forces. Okay? So this is why it's special. And of course it's an equilibrium. And the last point, which is cut off, is not actually really important. That all the forces are in the same plane. That's two-dimensional. But we don't worry about that. Anyway, let me draw that out for you. So what we're saying is we have a special situation in physics when there are 1, 2, 3 forces on something. This is actually quite a special situation. So let me draw the ladder that we had. So if you could draw this, please, as your example. Now this wall is smooth and the ground is rough. Okay, so here's my ladder. Right, so here's the first force, the weight. And then here's the second force. This is a reaction, I'll just call it S. Now when you think about it, there's really more than 3 forces here. There's actually 4 forces, because I'll do it in pink. There's one reaction force here from the ground. Yes? And why does the ladder not fall? Why does it not slip? Well, it doesn't slip because there is a friction or a drag, a friction force this way. Do you remember this word friction? Friction. Friction means like rough. So the ladder doesn't slip because there's a friction force on the ground. And there's also a reaction force going up. Now, we need to be careful with our vocabulary here. So we're going to introduce another word called normal reaction. Okay? So this reaction here, this one here is at 90 degrees. So we call this one a normal reaction. But you can put these two forces together to make one reaction force here, or, which I'll just call net reaction. Anyways, my point is still this: there are 3 forces. 1, 2, and 3. Although you can actually put 2 forces together to make one force. But I've made it into 3 forces. That's my point. Yep. So you might be thinking, well, what's the big deal if there are 3 forces? Why is that so special if there's 3 forces? No, nothing like that. More interesting. So, can I go back to my picture here in the slides? Notice in the picture that the 3 forces, 1, 2, 3, can you see how they all meet at one point? Can you see that? Now that didn't have to happen. It could have been like this. It could have been, for example, here is your forces, and then here is 1, let's say F1, F2, and then here is F3. So for example, this force will go here, this force will go here, and then this force will go here. So these ones don't meet. So what I'm saying is, it doesn't seem like they have to meet, but they do have to meet when there are 3 forces. And here's the proof. And the proof is really, really short. Not something on the exam, but I still think it's good to see. So imagine we have a shape. Doesn't matter what the shape is. And imagine there are 3 forces. Force 1, force 2, and then we'll put, I don't know where to put it. I'll just put it here. Force 3. Doesn't matter. Okay, so we all agree that. Actually, let me put it somewhere else. Let me just put it. I'll just put it here. Yeah, maybe I should put it pointing down. Let me put it here for the moment. Doesn't matter. Okay, we all agree that as long as these forces aren't parallel, they should meet. True? So they should meet. So we all agree that those 2 should meet. Now, let's have a look at this one. Let's call this distance here x. Now, I just said they should all meet. So what should the value of x be? Well, it should be 0. This distance here should be 0. This force should really go through it like this. So let's calculate x and see that we do actually get 0. So if I take this as my turning point, and if it's not moving, this force here, is it clockwise or anti-clockwise? Well, neither, because it's going through the turning point. What about this one, clockwise or anti-clockwise? No, neither, because it's going through the turning point. What about this one, clockwise or anti-clockwise? No, this one, well, we don't know that, 0 yet. So in my picture, which way is it? It's going, come on. Which way is it going? Clockwise or anti-clockwise? Anti-clockwise. It's going around this way. This force here is making it turn around this way. So you can't see. Going around like this. That's anti-clockwise. No, because the force is pointing to the right. It's making it turn this way. You know? If here's the shape and this force is going to the right, that's anti-clockwise.
You go like this.
If I go like what? Like this?
Well,
Show me.
yeah, it's pointing like this.
Wait, which way is it pointing? It's pointing to the right. Yeah, so put your force going to the right. You can only make it turn anti-clockwise. How can I make it turn clockwise? Impossible. So it's only going anti-clockwise. Yes? What is the turning force here? The anti-clockwise. Well, the distance is x and the force is F3. Now, how much clockwise turning force is there?
0.
Very good, 0. These two must be equal. Therefore, x equals 0. So in fact, I know that this force really should be here, that it too must be going through the turning point because the x is 0. So in other words, I have proved it. If you have three forces, 1, 2, 3, they always must meet at one common point. So if the system is balanced and not moving, and there are three forces, the three forces meet at one point. And this is when three forces act in the same plane on a mass in equilibrium, then all the lines of action meet at one common point. So this is called the three-force theorem. It seems very simple idea, but it's a very useful idea. That is, if you have three forces, you know that they all must meet at one point. Got that? Got it, yeah? Yeah? Okay. Right, so let's have a look at my first example. So write that down, please. A 10 kilogram ball of radius 5 centimeters hangs on a smooth wall by means of an 8 centimeter string, which is attached to the ceiling at, well, sorry, let me fix the English there, it's terrible English. A 10 kilogram ball of radius 5 hangs on this smooth wall by means of an 8 centimeter string, which is attached to the wall and to the ball. Well, there's the question there, you can write it down. A 10 kilogram ball of radius 5 centimeters hangs on a smooth wall by means of an 8 centimeter string, which is attached to the wall and to the ball. Find the tension in the string. Have you got the question written down? Yeah? Can I do it now? Yep, okay. So, this is what you have. Here's my wall. And then here's the ball. And I say that the ball is 5 centimeters. And what's the mass of the ball? 10, was it? 10 kilograms? So that means this will be 98.1 newtons, 10G. Now the ball is against the wall because it's hanging on the wall. So what's happening here? What's this called? Yeah, what's it called? Reaction. So there's a normal reaction, and I'll call it, let me write underneath, I'll call it or. Now, the reason this ball is on the wall is because there's a string. Now this is where it's interesting. I didn't tell you where the string was on the ball, did I? It seems like you have many choices. Maybe it's here, maybe it's here, maybe it's here, maybe it's here. You don't know. But actually, you do know. There's only one place it can be. Yeah, it has to be like this. Why does it have to be there? Exactly, because these two are going to meet here, so it must go through the center like this. Now, I think I said this distance here. What did I say this distance was? Actually, I don't remember. Oh, actually, how long did I say the string was? 8. So look, this is 8 centimeters, and how big is this? Let me draw the triangle. This is 8 plus 5. 8 plus 5, which is 13. And how big is this? 5. And by using Pythagoras, how big is this side? 12. So you can get this angle here. 5 is tan inverse 12 over 5. (67.4 degrees). So this force here is T cos, and this one here is T sine. I can't really fit it in, so I'll just draw it here to the side. This one is T cos phi, and this one here is T sine phi. I can't fit it in my picture. Well, maybe I can. If I zoom in. So this one here is T cos phi, T sine phi. Not too bad. Now, you actually have enough information to get to T. I know that T, too much colour, T sine phi must equal what? Yeah, which is what? 90.1. Yeah, the up force must equal the down force. Has to, because it's an equilibrium. So, 98.1 divided by sine 67.4, and you're done. T is 106 newtons. If I wanted to calculate the reaction force, I can do that as well. I can say, R must equal T cos 67.4, correct? So then that means R must equal T cos 67.4. I get R must equal 40.8 newtons. So I have the tension and the reaction force. Can I go back to the slides? Yeah, can I continue? You got that? Yep. Okay, see, where was I? So we did this. Okay. That one? Yeah, I just have the one example. Now relax. Before I let you do the questions, I just want to have a look at the ladder again.
What's that?
Just a ladder example again. So look, just to give you a little bit of help when you do the ladder question. Here is my beautiful ladder. Yes.
Wow.
Yeah, thanks.
Oh, that's cool.
Yeah, close enough.
And under the...
Nailed it. Right, so here is the weight, and then here is the reaction, I'll call this one OR, and then here is this reaction, I'll call this one here S. And let me give you some distances. So let's say the ground here, let's say this is 3 meters, and then let's make it easy, let's say this is 4 meters. So then from Pythagoras, how much is this? How big is this? 5 meters. So what I just want to do is, I just want to work out exactly where they meet, okay? So in pink here, this line, are we all looking? This line goes across here. This line goes up here. And so this one here must meet, right here. Now, I know how big this is. Maybe someone can tell me. Well, yeah, very good. It's a half tray. So this distance here is 1.5 meters. So if I draw another line up here, how big is this distance? 1.5. How big is this distance? That's 4. Yeah, 4. From here to here is 4. Now I can use Pythagoras to get this distance. Square root 1.5 squared plus 4 squared. So that would be 4.27. Now please look at this. Please look at this triangle I'm going to do in green. This is 4.27. How big is this side? 4. And how big is this side? 1.5. So if I want this angle here, I can say theta equals tan inverse what two numbers? 4 over 1.5. 4 over 1.5. So that means theta is 69.4 degrees. So I think this is a very interesting theorem, because even though I don't know the weight of the ladder, because notice how I just said W. Even though I don't know the weight, I still can know the exact angle here for the reaction, even though I don't know the weight. So I think this theorem, you get it in the exam, but it's not, they don't even make it this difficult in the exam. Usually in the exam they give you problems like this. You have a mass here, and it's being hung from the ceiling by 2 strings. So like for example, one here, and one here. So this here is, the one on the left, we'll call it a T, T1, T2. And what's here?
Wait.
The weight. So you know that these three must meet at this one point. So that's not really interesting, is it? So you can get a force this way, and then for T2 you can get a force this way, and then you can say these two must equal this, and this one here must equal that.
Or the two lines.
Yep. These white two lines here.
Or they are the same. They don't have.
Sorry,
Why they don't the same?
you don't like my pictures, I know. Sorry, let's try this again. So this one here is T1 sine, T1 cos, and then this one here could be smaller, T2 sine, T2 cos.
Yeah, why they don't the same?
Oh, why are these two not the same?
Yeah.
Oh, they will be the same if the angles are the same, but usually the angles are different, like for example 40 and, well, maybe not 40.
So when you want to equate it to W, you add them together?
Yes, yes. If the angles are the same, then yes,
Maybe the same.
maybe the same force, yeah. But it's never the same, because then it's too easy. Yeah. Okay. So, this is usually how it is in the exam. Or sometimes in the exam they do a ball. So you know, just like in my example, if there are three forces on the ball, they all must meet in the center. I lost one of my colours, now I have stupid white. I don't want white. What colour did I lose? My blue. Where's my colour wheel gone? Blue. No. Black. Red. Green. And what other colour will we like? Huh? I don't really want white. Ooh, maybe this kind of... Yeah. No, I like it. Alright. I won't use it then. So, just before you look at these, I just want to say what each system is. So the first one is, you have a mast and it's hanging from the ceiling with two strings. That's the first one. Like what I just drew. The second one is a rod, like this, and again there are two strings. One going this way and then one going this way. So it makes like a triangle. Okay? The third one is a cylinder. So this shape here is a cylinder. And what's happening in the third one is there's a small wall and there's a force pulling this, or pushing it if you want, pushing it, watch, and this force is going to push it over the wall. So if you think about it, the three forces are, first one is this pushing force, the second one is the reaction force on the wall, and the third one is the weight. Yeah. In fact, there's no reaction from the ground because when this is at the point of going over, you know, just as it's starting to move, it's not touching the ground anymore. And the last one is the ladder. The ladder up against the wall, like I drew. Okay? So I'll give, just try these for 5 minutes. Even if you get the first one though, that'd be great. So the first one, 1 and 2 I've seen in the exam before. Number 1 and 2 are exam style questions. 3 and 4, I haven't seen them on the exam, but I feel like that's the type that they could give you in the exam. Okay? So 1 and 2 are actual exam questions. So I don't worry about that. I'm too cool to worry about that. Alright, so you can start these and do them for 5 minutes.